Ladies and gentlemen, welcome back. So, last time we have talked about geometric models, or in particular we have talked about polygon models, and we have looked at how these shape representations are built and what the base primitives are they are built from. And then we have looked in particular into data structures which allow us to store such representations on a computer. Today we will talk about appearance modeling. So once we have the shape of such a geometric model, we need to assign attributes which tell us how this model should appear on the screen when we finally draw it on that screen. And one of the most important appearance attributes, of course, is color. And before we talk about how color is assigned to such a model and how then color is used in the process of drawing the model to the screen, we will first have to talk about how color is specified. And in this lecture throughout the remainder of this lecture here, we will make use of the so-called RGB color model, the red, green, blue color model. So in this color model, color is defined as a superposition of the three primary colors, red, green, and blue. What does primary colors means? It means that by means of these three colors, I can essentially build every color that is perceivable by the human perceptual system, and non-single color of these three primary colors can be represented by the other two colors. The thing I said first, that these three primary colors, red, green, and blue, can produce all the perceptual colors, is not entirely true. It can be shown that there are colors which cannot be represented in that RGB color model. If you would also like to represent these colors, then you would have to switch to other color models. Just that you have heard the name, the CIE model, for instance, is a color model that can then in fact reproduce all the perceivable colors. As I said, we will stick to this so-called additive color model because the red, green, blue color components are just added together or imposed on each other to build the final color. Then you see here on the right hand side that image where you have the so-called RGB color cube. So we start here in the lower left front corner. That is the color black, so to say, where we have no red, no green, no blue. If we then add a certain amount of red to that black, then we essentially go along this axis in that color space. If we add a certain amount of green, we go into that direction. If we add a certain amount of blue, then we go into that direction. And in this way, by just specifying what are the amounts of red, green, and blue colors that are then added together to form the final color, we obtain the color we are interested in. So once now we know how color is specified, we need to talk about how colors are assigned to the polygons. Remember, we are talking here about polygon models. So polygon models are the models which are used in order to describe the shape of our objects. And we have heard about or what kind of base primitives these polygon models are comprised of. Now we have vertices, and then we have edges connecting these vertices, and from these edges we build polygons, for instance, triangles. Now, if we have colors and we want to assign colors to such a polygon model, then we assign the colors to the polygon vertices. We do that in the modeling stage, and we specify these colors just as an additional so-called per vertex attribute. And then we have two different options. The first option, that is option here, and that is what you see here on the left-hand side, is that you just take the polygon colors and you then smoothly interpolate these colors across the triangles. And this gives the smooth appearance we see here on the left-hand side. You could also interpret the colors in a different way. No? You could also say, okay, well, I do not smoothly interpolate the colors across the triangles or across the polygons, no? But I just pick one particular vertex, and then I say that the color of this vertex should be the color that is assigned to all the points in a certain vertex that shares, in a certain face that shares that vertex. And that is what we see here on the right-hand side. Now you see we don't have a smooth color distribution across the surface, but we see the face structure, and that comes from a unique color that is assigned to all the face points, and no interpolation here is involved. That is the option 2, which we could in principle apply. So first of all, once we have these colors, let us briefly talk about how we extend the shared vertex, or the so-called indexed face set representation we have introduced last time. So you see how the color goes into that representation here. So in fact, all we have to do is we have to store for each of the vertices now one additional attribute, namely the RGB color components that make up the color of that vertex, meaning that we simply extend the vertex list. Instead of just storing the coordinates of every vertex, we now also store its color, and the other array we have introduced, the face array or the triangle array remains unchanged because the topology of the geometric model is not affected. So now comes the question, how do we make triangles or triangle meshes look solid? So what we see here on the left-hand side is the wireframe representation, where we only draw the edges connecting the vertices in our geometric model. And what we see here on the left-hand side is now a visualization of the very same geometric model, but now the faces appear opaque. We have also some illumination on these faces, which we will discuss later on. So now we need to think about how we actually fill the triangles. How do we make the triangles look opaque? And we want to fill them with the colors that have been assigned to the vertices. And this process is called the shading process. So shading transforms the, so to say, geometric model, which are just given by the vertices, by the edges, by the faces, and additional appearance attributes like color, which are assigned per vertex, and then uses these attributes in order to generate an image of the model where the triangles are considered to be solid. So they are filled now with the colors that have been assigned to the vertices. And we will now look in particular at this shading process in order to understand how the so-called rendering process, which is the process of taking such a geometric model and then producing an image of that model, which uses all the shape and appearance properties that have been described. And in order to understand that rendering process, we need to know how that shading process works. So, and to understand shading, we first have to think about how a polygon model is brought to the screen. And that is exactly what I just said. That is what we call the rendering process. The process of taking the initial geometric model in whatever form it comes, taking the associated appearance attributes, and then bringing this model to the screen, or more precisely, bringing an image of that model to the screen. So what we have vertices and edges, and the vertices have coordinates in 3D space. And you see 3 successively refined models of the very basic very same shape here in the bottom. So now, how do we display a polygon model? no? And that now brings us, so to say, to the core of rendering. So what we see is always a 2D image of a model. And the first question we can ask, so what is such an image? No? So an image, I think we all know, is simply a two-dimensional array. The elements in this array are called the pixels, the picture elements. Each pixel has a color, and this is then the color which is drawn on the display device by the display system. So the pixels are arranged in a 2D pixel raster, the 2D array, which we, for instance, see here. Now we can think about that every of these little quadrilateral elements is essentially a pixel. And what now the so-called rendering process needs to do, it has to determine what is seen when looking through one of these pixels, or let's say through all of these pixels into the scene. And then the color of the point that is seen when looking through a pixel, that is then the color that is assigned to that pixel. And being more precise here, how do we determine what is seen through a pixel? Now, a pixel is essentially an aerial element, so it covers some area in the 2D image plane. But what we actually do is we just ask what is seen through the center of each pixel. And once we have determined the color that is seen when looking exactly through the center of each of the pixels, then these colors are assigned to the pixels and finally displayed. You see here on the right hand side how we actually could do this via a so-called ray-based approach. What does it mean? It means, okay, once we know where that, so to say, virtual screen is located in 3D space, if we know where our objects are located in 3D space, and if we know from where we now look into the scene, that is the so-called eye point or camera point, which tells us that, then what we can easily do is we can compute for every pixel in that screen the center of that pixel, meaning that we now have 2 points. We have the center point, we have the eye point. From this we can then spawn a ray. And we can now simply take this ray, we can shot this ray into the scene, and we can then intersect that ray with all the objects in the scene. And of all the intersection points that are computed, the one closest to the eye point, there will then be the one which color is seen through that pixel. Now we will see in the remainder of this lecture that what I have just illustrated here is actually not the so-called rendering process that is realized when you do computer graphics on a graphics accelerator. But I think if you first of all think about that kind of ray-based rendering, then it becomes pretty clear what we are actually trying to compute and how in principle we can compute that. So always think about also later on, if you come to a different rendering process, always also think in terms of rays. Think about what the situation is. You have a position from which the rays are started, the eye point or camera point. You have a screen, which is, or a virtual view window, which is somewhere positioned in 3D space. You have a pixel raster. You say, for instance, that you want to use 512 times 512 pixels, covering that virtual view window. And then you have everything you need in order to define the rays going from the eye point through the pixel centers. And if you now have objects in the scene, you can then intersect the rays with each of the objects. And once you have the intersection points and someone tells you what the color at these points is, then of course you can immediately take that color and assign it to the corresponding pixels. Okay, it is clear that what happens here has to be repeated whenever either the eye point changes or the object changes. Now, if you place the screen at different positions or orientations, the object can be seen under what we call different perspectives. No? That is exactly what you see here on the right-hand side. You have the very same object. No? There's some coloring on the faces of that cube. No? And then depending on from where you look at this object, of course, the object appears differently. No? And that means that for each new view, and a new view is essentially, so to say, a view in which either you as the observer, or the camera changes its position, or the object changes its position or orientation. And whenever this happens, then it has to be determined anew what is seen through the pixels in the screen. That means that, many times per second, if you have an animation, if something moves, you have to repeat the so-called rendering process. And that means that creating one single image should be very efficient in order to not, or in order to get a continuous, so to say, image update rate. So, shading is now the process which makes a triangle look solid. And in order to do so, the renderer, this process which creates an image of a given geometric object with associated appearance attributes, this renderer has to now give color to the points on the triangle. If you go back to the example with a ray-based approach, once the intersection between a ray and the object is found, then we have a location in 3D space, which is the location on the object against which the ray was intersected. And then we have to determine what is the color at this intersection point. So, that is something the renderer has to determine. And of course, the renderer also needs to figure out which are these points which are actually seen through the pixels. Again, using the ray-based approach, the renderer could just throw rays into the scene. First of all, build these rays and then intersect these rays with all the objects in the scene. However, as I said, at least the rendering process as it is implemented on current graphics card is not a ray-based approach, so the renderer determines the point that are seen through the pixel in a different way. Once these points are known, once we know the colors of these points, then of course these colors can be assigned to the pixels. And now comes the question how the renderer actually determines the points on the object that are seen through the pixel centers. Let us illustrate this. Let us assume we have a triangle like the one here that is comprised of 3 vertices, and at each of the vertices we have assigned a color C0, color C1, color C2. So now let's assume we are looking at this triangle. Now this triangle lives somewhere in 3D space. So the vertex coordinates are just coordinates in R3. So it lives somewhere in 3D space. And now let's assume we are taking that discrete pixel raster, that raster which has a resolution which we have chosen. And now imagine that we are holding that raster in front of us. And now we are simulating what do we see when looking through that raster here onto the triangle. And more precisely, we want to determine what do we see when looking through the pixel centers of the pixels in that raster at the triangle. And in this particular case here, we see if we just go over all the pixel centers, and then we only draw those pixel centers here through which we actually see something from the triangle, then you can imagine that we are almost done. So we have now the pixel centers. We could in principle, let us again go back to the ray-based approach. We could now take a ray. The ray starts at the camera position. The ray then goes through the pixel centers, and the ray is then intersected against the triangle. And the point at which the intersections occur, or the intersection occur between the ray and the triangle, that is then the point of the triangle we see when looking through that pixel center. And we see here, we don't see here. Let's just go to the next example. First of all, we see here that now if we take the colors of the triangle points that are seen through the pixel centers and assign them now to the pixels, then in gray we have all the pixels that will now receive a value. And you see, for instance, that here we have a pixel that is also, so to say, covered by a part of the triangle, but because if I pick the pixel center here, and if I would now trace a ray through that pixel center, that ray doesn't hit the triangle. It is assumed that the triangle doesn't have a contribution to that pixel. Okay, what we can now do is we can take the very same triangle, and now let us assume that we shift away that triangle from the camera. So really think about this in the following way. So you have a little triangle. That triangle is placed in the space in front of you. And now you just move that triangle away from you. And it's clear, because of the perspective, that now this triangle appears smaller. Or in other words, the triangle covers less space in this image space. And if we now do the very same which we have done before, we again take our pixel raster, which doesn't change, and now we look at that triangle, which is the very same triangle as we see on the left-hand side, but just at a larger distance from this virtual view image. Then we see that now, for instance, in this situation, only 3 pixels are actually covered, or in other words, only through the center points of these 3 pixels here, when I would use a ray-based approach, I would hit the triangle. For all the other pixels, I see that if I take a ray, let it go from the camera through the pixel center points, then they will not hit the triangle, meaning that these pixels remain empty. Okay, so you see, depending on the size of an object, in this particular case here, the size of a triangle, but also its orientation, and in particular its distance to the view plane, the number of pixels that are actually covered by that triangle, or in other words, the number of pixels for which the rays going through their centers will hit the triangle, differs significantly. Okay, but you see here, that is the basic approach, you could say. If we would not know anything else and someone would ask you now to fill these pixels, you would already been able to do that. Because all you would have to do is, what I just said, take the camera position, compute the pixel centers. These are points in 3D space. If someone tells you where that pixel raster is positioned in 3D space, then you have a ray, and then if you have a triangle, just intersect that ray with a triangle, compute the intersection points, and at least you have all the points on the triangle that, so to say, leave their footprint in the current pixel raster. Here are the 3 pixels that are actually being determined as they see, or through their center points, we see the triangle. So now the question is, what is the color of a point on a triangle? So far we could say, okay, we have now the location. or the position in 3D space of the intersection point between the ray and the triangle, but we do not know what the color at that point is. And now we have two choices. The first choice, that is, so to say, that was the second choice on the slide when we introduced that color shading process or color interpolation process, where we said, okay, we could say, if we have an intersection with a triangle and we know which are the three vertices which make up that triangle, I just pick one of the vertices and the color of that vertex is assigned to all the triangle points. That is what we see in this image here and in the image here on the right. And this gives us a piecewise constant color across the polygons, because the color only depends on the color of that one single vertex I have picked, and it is the same for all the triangle points. Yeah, that is sometimes what we want to achieve if, for instance, we are interested in still seeing the underlying polygon model. Then such a constant color per polygon is often something we do. But in general, of course, we rather would like to have a smooth variation of the colors, and that is what you see here. We see here in the two images the very same polygon models we have at the top, but now we let the colors smoothly interpolate across the polygons so that we get the appearances we see here at the bottom. The question now is how can this be achieved? And that brings us then to, so to say, the core of the shading process. The shading process now tells us for a certain point on the triangle, in this case here, that black point, what is the color at that point here? And we assume in this example here on the left that the colors which are assigned to the vertices are 0, 1, 1, meaning we have red here. Then we have 0, 1, 1 here at the second vertex, meaning that we also have red here. And also at the third vertex, we have red. Now, let us assume here that the color components are from the interval between 0 and 1, meaning that we add full red, so to say, and we have no green, we have no blue, meaning that the color of these vertices is just plain red. So, and if I would ask you now, so what is the color at the dark point, which we supposed to live in the triangle, and then you would probably say, okay, because all of the three vertices have been assigned a color of red, then, I mean, there can be no other choice than also giving a red color to that black point, which is in the triangle. And that is, correct. That is exactly what we expect, and that is also exactly what we would do. However, let us now have different colors. Now we have a red, which is assigned to the vertex 1. We have a blue, which is assigned to the vertex 2, and we have green, which is assigned to the third vertex. And now the question is, okay, what is the color now at this point here? And I think intuitively it is clear what we expect. At least if we expect a smooth color variation, then we would expect that the color at this point here in the triangle is some mixture between the red and the green and the blue from the three vertices. But of course, we have to be precise about how this mixture is actually computed. And this brings us then to the smooth color shading or the smooth color variation across the polygons. And that is what we now achieve by performing a certain type of interpolation, the so-called barycentric interpolation. Now you see this here on the right-hand side, now where we have a light blue at these two vertices, where we have a rather dark blue at this vertex, and now we see that we have a very smooth color variation across the triangle, going from the light blue in this area here towards the dark blue in this area. and you don't see any abrupt color changes. No, you don't see any color discontinuities. It seems that we have a very smooth transition of the color from the vertex colors into the interior and to the respective other colors. And that is essentially also what you see here in these two examples. There are differences in the color, or especially in the reflection, the illumination contributions on these two shapes here in the middle and on the right. We will go into the details of these two models, not the models, but the way they have been shaded later on. For now, let us just emphasize again what we have here on the left-hand side, the piecewise constant color per polygon. And in the middle and the right-hand side, you have a smooth variation of the colors across the polygons. Yeah, now we need to think about how this smooth color variation is computed. And again, as I said before, this brings us now to the so-called barycentric interpolation. So what does barycentric interpolation mean? And really keep this in mind, try to understand it, because this is an operation that is really at the core of every rendering process, because it's essentially an operation that tells us how to obtain a smooth variation of parameters that are given at the vertices of a triangle. So let us become more precise. Let us assume again we have a triangle here. This triangle here is made of 3 vertices, P1, P2 and P3. Now again, these are vertices in 3D space. And to each of the vertices we have assigned a color, C1 and C2 and C3. So, and now let us pick an arbitrary point P which is in that triangle. Okay? And the question now is, if we have that point P, what is the color at that point? And let us go back to the example from before, where we used that ray-based approach in order to imagine how in principle the rendering process could go. Now we said that we take the rays, we intersect the rays against the triangles in the scene. And that would then give us an intersection point. So P could be an intersection point between a ray and that triangle. And now at that intersection point, we need to determine the color. And because colors are assigned per vertex at the vertices P1, P2 and P3 of that triangle, we now need to use some form of interpolation in order to bring the colors from the vertices to that point P in the interior of the triangle. So what we know is that every point P, and keep in mind, every point P has an X, a Y and a Z coordinate. And of course P1 and P2 and P3 also have X, Y and Z coordinates. And now what we can do is, and we can even prove this, that every point P which is in the interior of a triangle that is made from vertices P1 and P2 and P3 can be expressed via this linear combination of the vertices P1, P2 and P3 with weights alpha 1, alpha 2 and alpha 3. And in addition, if we sum up all these alphas, then their sum is equal to 1. Okay, so you can easily prove this by just asking the question, so if I would give you such a triangle, how would you actually represent that point P? And you would probably say that P can be constructed as we start, for instance, at P3, and then we go a little step, or we go some step along the edge from P3 to P2, like for instance to here. And then we make a step into the direction of the edge from P3 to P1, and that would bring us then to the point. And if you write that down And then you see immediately that after some reformulations, you arrive exactly at the barycentric coordinate formulation we see here. And just saying this again, what it means, assuming that we have the coordinate of P, it is clear that we also have the coordinates of P1 and P2 and P3, because these are the coordinates of the triangle against which we have intersected, for instance, our ray. Then this point P can be expressed via these so-called barycentric coordinates alpha 1, alpha 2, and alpha 3 in the form we see here in this equation. And even more than that, we know that the sum of these three barycentric coordinates is equal to 1. So now, if for the point P we have now found the barycentric coordinates alpha 1, alpha 2, and alpha 3, then everything becomes very simple, because then we can use exactly these barycentric coordinates and interpolate whatever other attribute has been specified at the vertices. In our example here, the colors. No? And that is now interesting, and that is good, because it means I only have to compute these barycentric coordinates once, and once I have them, once I know what these barycentric coordinates, we could also interpret them somehow as weights. Once we know what the weights of P1, namely alpha 1, of P2, namely alpha 2, of P3, namely alpha 3, are for that particular point P, then I can reuse these weights in order to interpolate whatever other attribute is given at the vertices, in this particular case, the color. And now the remaining question, of course, is how do we actually compute these barycentric coordinates? We have an inside triangle criteria. I will come back to this here on the right-hand side a little later. Let us first now talk about how these barycentric coordinates can be computed. So, and they can be computed as given here. So alpha 1, the weight of the vertex P1, is computed as the area of the triangle that is formed by the point P, by the point P2, and by the point P3. That is exactly that triangle here. And we take the area of that triangle and divide it through the area of the entire triangle. And that gives us then alpha 1, which is supposed to be the weight for P1. And for the other alpha values, now the computation is analog. So in order to determine alpha 2, that is the vertex here, you take the area of the so-called opposite triangle, which is the triangle made from P, P1, and P3, the area of that triangle here, and you divide it through the area of the entire triangle. And the very same for alpha 3. You take the area of the triangle which is made from P, P1, and P2. Now we have this area, and you divide it through the area of the entire triangle. So this is how you compute the alpha values. So you see immediately, because at least for points inside a triangle, the areas of the sub-triangles here, they can never become larger than the area of the entire triangle, meaning that the barycentric coordinates are bound by 1. And you also see that the area can never become less than 0, meaning that the barycentric coordinates are bound by 0. Now, if you, for instance, take the point P here, and now you move that point here so that it comes to lie exactly on that edge here, then you see that the area of this triangle here, so to say, has collapsed to 0. And then if you now compute the barycentric coordinate alpha 2 for the opposite vertex P2, then this barycentric coordinate would just be 0. No? And that is somehow what we expect, because what then happens is that the color at that point here does not depend on the color of P2 anymore. It only depends on the colors of P3 and P1. And in fact, the whole barycentric interpolation then becomes a linear interpolation between color C3 and color C1. And on the other hand, if I take that point P here, and if I move it now onto P2, then it's clear that the triangle that is formed by P and P1 and P3 is now exactly the initial triangle. So the barycentric coordinate for P2 will now be 1. And because we know that all the barycentric coordinates sum up to 1, it is immediately clear that the other two barycentric coordinates must be 0. And that is exactly what we expect. Because if I have a point which is sitting exactly here at P2, then I want that only the color of P2 is responsible for the color at that point P, and the other two colors C3 and C1 should not have any effect. That is exactly given then by the barycentric coordinates of 0 for P1 and P3 and 1 for P2. So there's one thing, and this is also nice about the barycentric coordinates. Now we have seen that if we compute the barycentric coordinates in a way we have done it here, then when for all the points which are in the interior of the triangle or are sitting on the edges of the triangle, the barycentric coordinates will always be in the interval between 0 and 1. And this means that this then becomes the so-called inside triangle criteria. And now you might ask, okay, so can it happen that the barycentric coordinate is larger than 1 or less than 0? Yeah, and this can happen because what you can do is just the following. You could just pick a point here, for instance. This point should still live in the plane in which that triangle lives, but the point now is outside the triangle. And in fact, also for this point, you can compute the barycentric coordinates. And if you do it in the way we have done it here, you will see that the barycentric coordinate then either becomes less than 0 or larger than 1. The only assumption we have to do now is the following, that if a point, for instance, this point P here, moves now towards this edge, we have already seen that the area of that triangle becomes smaller and smaller and smaller, and once that point P here sits exactly on this edge, then the area of that triangle is exactly 0. And now we can say if that point moves further into the exterior of the triangle, then that area here, or that triangle here, gets an area again, but now what we do is we interpret this area to be negative. Yeah. So whenever a point is crossing an edge, we interpret this area to be of the resulting triangle to be so if it crosses the edge opposite to the vertex for which we want to compute the barycentric coordinates, then we interpret the area to be negative, and then we also obtain negative barycentric coordinates. And the good thing is, once we have a point with negative barycentric coordinates, or also with barycentric coordinates larger than 1, we can immediately tell that this point is not inside the triangle. Now, just for the sake of completeness, you would not even need what we have discussed here, because you see here immediately what we have. Now, if I would write down this equation here, for the x, the y, and the z components of the point P, P1, P2, and P3, then we see that we have 3 equations, and here we have even a 4th equation, meaning that we have a system of equations and we have 3 unknowns. And that even means that we need to get rid of one of the equations, and that can easily be done because we know that a triangle is a planar structure in a plane, and a plane is essentially a 2D structure, meaning we could just interpret these points here in the plane in which the triangle lives. That would then allow us to get rid of one of the 4 equations. At the end, we would have 3 equations for the 3 unknowns, alpha 1, alpha 2, and alpha 3, and we could simply solve that system of equations in order to obtain the unknown alpha values. So keep this in mind mathematically. And this, by the way, if you then solve that system of equation via, for instance, Cramer's rule, then you will see that the solution will be exactly what we introduced here, but we wrote it down in a slightly different way. Okay, so yeah, keep this in mind, the barycentric interpolation using barycentric coordinates as weights for the vertices. And then once we have these barycentric coordinates, we use these coordinates as weights for whatever attribute I have specified at the vertices, like the colors. But we will see that we can also use vectors which are specified at the vertices. We could use reflection properties. We could use, we will later on come to texture coordinates. Whatever we specify here at the vertices, once we have the barycentric coordinates, we can just smoothly interpolate these attributes across the triangles by using barycentric interpolation. So yeah, and now we are almost done. So here we have again the wireframe representation of these of the scene. We have I think looked at in the previous lecture already. And now if you give color to the polygons in that scene, then the whole thing looks like this. And we see immediately that color helps significantly to improve the degree of realism of our scene. And yeah, by now we know how coloring is performed. We assign colors per vertex or to the vertices of our polygon model. And then the renderer needs to determine at every point of the model or of the scene that is seen through the pixel centers by means of barycentric interpolation, what is the color at this point, and this is then the color you draw on the screen. Yeah, next time then we will come back to this image and we will look in a little more detail at this image, because we will then immediately realize that the color distribution which I see here, for instance, on the ground, can hardly be achieved by just assigning colors to the vertices. So there must be involved some other mechanism, and this will then bring us to what we call texture mapping.